sponsored by Surfshark VPN. Although nuclear energy is reliable, powerful, and a clean energy source, it's still not considered the go-to solution in the big energy transition we're experiencing right now. Solar, wind, and hydro are getting all the attention. Nuclear reactors are big, expensive, and take a long time to build, even longer to get permitted, and there's also the nuclear perception issue to overcome. So what if we could make them smaller, portable, cheaper, and safer? Small modular reactors are getting a lot of interest, with the first versions coming online in China and new locations popping up in Canada, as well as ex-SpaceX engineers that have made things even smaller to a micro-reactor scale. Could this be the future of nuclear energy? I'm Matt Farrell. Welcome to Undecided. In December 2020, I published a video exploring one of the rising stars of modern nuclear technology, small modular reactors. And at the time, we still hadn't seen any SMR-based power plants in commercial operation. Several projects were being developed around the globe, but have been running into roadblocks. The Oregon-based NuScale, which has spent millions in SMR development, is facing regulatory issues in their project involving a 12-module, 540-megawatt power plant. Since my previous video, there have been several updates and new projects that are worth touching on, like the Chinese SMR demonstration project I explored in 2020. At that time, it hadn't got off the drawing board, but the project finally kicked off construction in July of 2021. Ex-SpaceX engineers have also been making some news, but first let's quickly review what SMRs are and why so many people keep pushing for nuclear as the solution to our energy problems. I see it all the time in my video comments. SMRs operate based on nuclear fission, just like traditional nuclear reactors, where neutrons split atoms, releasing energy. As the atoms split into smaller atoms, a few extra neutrons are released, which in turn split more atoms, feeding the chain reaction and maintaining the cycle. There are basically two designs of SMRs, thermal neutron reactors and fast neutron reactors. The difference between the two, which you might have guessed by the word fast in the name, is the speed of the neutron's flow. Neutrons of thermal neutron reactors move at a speed of 2.2 kilometers a second and contain an energy amount equal to 0.025 eV, where EV means electron volts, which is the kinetic energy gained by a single electron speeding up through a potential difference of 1 volt in a vacuum. On the speedier side, fast neutron reactors operate with a neutron flow at speeds around 50,000 kilometers a second and an energy amount in the MeV scale, where MeV stands for mega electron volt. That's 1 million electron volts, so yes, they have a bit more punch. Now, fast neutron reactors utilize liquid metal for cooling and don't require a moderator. Thermal reactors usually use water for cooling and do need a moderator. However, what really sets SMRs apart from traditional nuclear reactors is, again, right in the name, their smaller size and power capacity. While conventional reactors are huge, built on site, and can produce up to gigawatts of power, SMRs are much smaller, generate less than 300 megawatts, and can be built off-site. The enormous size of conventional reactors makes the construction of nuclear power plants complex and slow, taking about 6 years to be completed, which also results in higher costs. SMRs can be built much faster, requiring less staff for location assembly, maintenance, and operation. Their modularity, smaller size, and the possibility of in-factory construction opens up opportunities for the installation of multiple units on the same site, as well as simpler component transportation and standardizing manufacturing. When you can commoditize manufacturing, the prices will drop. And when it comes to safety, manufacturing SMRs include the latest safety features and security requirements. SMRs have smaller cores, which opens up space for the integration of more components into a single vessel, like the nuclear stream supply system. Their modular design results in simplified and safer systems, implying reduced severe failure modes, shielding requirements, and reducing off-site emergency planning zones. Now, NuScale's SMR, for example, can passively cool itself utilizing natural water circulation without needing additional coolant or power supply. On top of that, its design is immersed in water to assist in cooling the reactor during unusual conditions, not to mention the specific valves that instantly release heat from the reactor vessel during an emergency. That all sounds great, but what about putting that into practice? Well, there's been some interesting developments on that recently. But before I get to that, I'd like to thank Surfshark for sponsoring today's video. I always recommend using a VPN when using public Wi-Fi, but VPNs can be very useful even when you're at home. A lot of online services use some pretty sophisticated commercial targeting and tracking, and a VPN can protect you from that. Surfshark's CleanWeb does a great job blocking ads, trackers, and malicious websites, making it safer to use the internet even at home. And you can even make it look like your IP address is coming from a completely different country. This can come in handy if you want to stream a video that's only available from a specific location. One of the best parts of Surfshark is that it's easy to set up on all of your devices, whether that's iPhone or Android, Mac or PC. Surfshark is the only VPN to offer one account to use with an unlimited number of devices. Use my code to get 83% off plus 3 extra months for free. Surfshark offers a 30-day money-back guarantee, so there's no risk to try it out for yourself. The link's in the description below, and thanks to Surfshark and to all of you for supporting the channel. Now back to the latest developments in SMRs. At the end of 2021, the world's first commercial onshore SMR was started up in China after 9 years. The 200 megawatt Unit 1 reactor manufactured by China Huaneng Group Corporation was connected to the grid in northeast China's Shandong province. This is the world's first pebble bed modular high temperature reactor cooled with helium gas instead of liquid water. Using a gas as the reactor coolant allows the core to heat up to about 1800 degrees Fahrenheit, which can't be achieved using water. Helium is extremely stable and non-flammable, so it's a great coolant. The company already has a second unit scheduled for 2023, but the project's cost hasn't been disclosed. And according to Tsinghua University research, the commercialization process should cut the cost of each reactor by roughly 60%. Just this past December, GE Hitachi Nuclear Energy and Ontario Power Generation in Canada are working on the new Darlington nuclear site. The plan is to use a BWRX-300 SMR for the project. I love the names of these products, which uses passive safety features and is cooled by natural water circulation. OPG had also considered Terrestrial Energy's integrated molten salt reactor and XZ100 Energy's high-temperature gas-cooled reactor. The BWRX-300, a name that rolls right off the tongue the more I say it, is projected to have up to 60% less capital costs per megawatt when compared with a typical water-cooled SMR. In addition, it can be built in 2 to 3 years when combining its modularity with the use of open-top building techniques, which results in a 90% volume reduction in plant layout. The open-top technique is pretty much what it sounds like. The walls of the containment facility are built first, but the top is left open. This makes it easier to use large capacity cranes to lower the components in from the top. According to a study developed by the Conference Board of Canada, a 300 megawatt grid scale SMR could result in thousands of direct and indirect jobs from the project development all the way through decommissioning after 60 years of operation. In addition, a report from PwC Canada estimates the project could generate $1.9 billion Canadian in labor income, more than $750 million in federal, provincial, and municipal tax revenue, and $2.3 billion in gross domestic product over its lifespan. The project's expected to be completed as early as 2028. Comparatively, a report made by Hatch showed that using Terrestrial Energy's IMSR 400 power plant, which is composed of 2 integrated molten salt reactors and generators that could deliver 390 megawatts of power, could generate nearly $6.6 billion of GDP for Ontario and $7.9 billion of GDP during its lifespan. However, the design and construction of their model would take 9 years. Now, while these are small, what about going even smaller? Another alternative to conventional nuclear power plants that's been gaining attention recently is microreactors. This compact type of reactor can generate from 1 megawatt to 20 megawatts, being able to operate either connected to or islanded from the grid, or as part of a microgrid. They're 100 to 1,000 times smaller than a traditional nuclear reactor and have power rates from 10 to 100 times lower than an SMR. If SMRs can be easily transported by trucks and ships to their final destination, imagine what this technology could bring to the table. Now, microreactors could be easily integrated with renewables and microgrids used to restore power cuts from natural disasters, and can be simply moved from one site to another. In addition, when compared to current commercial reactors, microreactors use low-enriched uranium with uranium-235 and higher concentration. These reactors can run for up to 10 years without refueling, and due to their extremely small reactor volume, they're safer to operate. In the US, former SpaceX engineers have launched the startup Radiant. They're developing a micronuclear reactor rated at 1 megawatt that could provide power for 1,000 homes without needing an external water supply. The microreactor uses helium for cooling and has remote monitoring and maintenance functions, which reduces the risk of damage. Radiant has received $1.2 million from private investment. However, the technology is still patent pending, so there isn't much technical information and specifications available to the public yet, so we couldn't find more details there. So as exciting as all of that is, what's holding all of this back? Why not just go nuclear? The main challenges surrounding the SMR market are related to complicated licensing and regulatory guides, codes, and standards of practice, and legal frameworks around the globe. But beyond the regulatory challenges, there's also the cost. While conventional nuclear power has a levelized cost of electricity, or LCOE, ranging from $131 to $204 per megawatt hour, SMRs have an LCOE of $120 per megawatt hour for a typical market in the US, Europe, or Japan. Now, this figure is lower than traditional reactors, but still much higher than the LCOE for thorium reactors, which reaches about $53 per megawatt hour with a 30-year lifespan. On the flip side, the ability to incrementally add modules to an installation reduces both upfront investment and capital risk of SMRs compared to other nuclear technologies. However, compared to solar, wind, and hydro, you're looking at something in the range of $26 to $50 per megawatt hour. Even wholesale solar plus battery systems are in the range of $85 to $158 per megawatt hour. So nuclear isn't the slam dunk there either. Now finally, the biggest issue with nuclear power is how to dispose of the waste. What do we do with the radioactive waste from nuclear power plants, which can be extremely dangerous for thousands of years? Just here in the US, for example, 90,000 metric tons of nuclear waste is waiting to be permanently disposed of, but there aren't any permanent geological repositories in operation yet. In the meantime, the containers storing all of that radioactive material degrade. A more permanent solution proposed by scientists is to vitrify nuclear waste so that the mixture provides some shielding against radioactive leakage. However, this process is complex and still has uncertainties. This is where thorium reactors can contribute to nuclear waste storage. As I explored my video revisiting thorium reactors, their waste is radioactive for about 500 years, while the waste from conventional nuclear reactors is still radioactive for thousands of years. And not to sound like I'm banging the nuclear is scary drum too much, it's an extremely safe power source. When we look at safety data from power sources, nuclear power has considerably lower death rates from energy production per terawatt hour when compared to other power sources. While nuclear power has a death rate from accidents of 0.07 per terawatt hour, widely used energy sources like coal and oil have 24.62 and 18 respectively, which is yet just another reason why we have to move beyond them quickly. Now, although SMRs and microreactors can address several problems of conventional reactors, and the SMR market is expected to grow at a rate of about 15.8% until 2030, there are still many challenges to overcome. There's been some good progress over the past couple of years, and some exciting ones on the horizon, but whether SMRs and microreactors will be the mainstream technologies for nuclear power isn't a sure thing. So what do you think of SMRs? Will they gain a foothold and become part of our energy mix? Jump in the comments and let me know. If you have knowledge on this or you work in the industry, please share your experience so we can all learn more together. You can also join my Discord server and talk to other members of the community. The link's in the description. And thanks as always to my patrons, and a big welcome to new Supporter Plus member Glenn Campbell. All of your direct support really helps with producing these videos and to reduce my dependence on the almighty YouTube algorithm. And speaking of that algorithm, if you like this video, be sure to check out one of the ones I've linked to right here, and subscribe and hit that notification bell if you think I've earned it. Thanks so much for watching. I'll see you in the next one.